Hi, this is Dr. Viv, and we shall be discussing some basic vector addition. The problem I have here is you have a particle or a person walking a certain distance, let's say 5 units. It can be 5 miles if you like, at an angle of 30 degrees with the y-axis, and then you turn around and walk another 7 miles at an angle of 30 degrees like that. Then you turn around and turn 45 degrees to the south and walk another 6 miles. Well, the question is, how far are you away from your starting point, and in which direction should you be moving, and how long of a distance do you have to cover to get back to your starting point? To solve a problem like this, you notice that these vectors are specified in polar coordinates. That is to say, we are given the magnitude and the direction. So let's write down these vectors in polar coordinates first. Let's call this vector A. We'll call this vector B. We'll call this vector C. So I wish to write A, B, and C in polar coordinates. My convention for polar coordinates is that pointy brackets. So it's 5 units, comma, 120 degrees. And I'm measuring the angles counterclockwise from the positive x-axis, so I have to, that's not 30, but rather 30 plus 90, or 120. Likewise, I can write down what B is. B is going to be 7 is the magnitude, and the angle is going to be 30 degrees. The vector C would be magnitude 6. Now observe that this is actually below the x-axis, the x-axis being that dotted line there, so we have to write it as negative 45 degrees. Alternatively, you can add 360 to negative 45 and write it as positive, whatever that big angle is. I don't care to do that. Now before you can add vectors, you have to convert them into Cartesian form. So that's the next step. Let's convert all these things to Cartesian form. So the formula there is that the x component is going to be the magnitude times the cosine of the angle. So it's 5 times, I think I've run out of ink on this one. It's 5 times cosine of 120 in the I hat direction. Now remember that you have unit vectors in the x and the y direction. The unit vector in the x direction is known as I hat, and the unit vector in the y direction is known as j hat. And if you had a 3-dimensional problem, the unit vector in the z hat direction would be k hat. So the only difference between 2D and 3D is that you have an extra term in this Cartesian decomposition of the vector. Now when you write the vector's y component, it's going to have the sine of that angle, which is 120 degrees, times j hat. Okay, so this can be written out. I remember that cosine of an angle in the second quadrant is negative, so that's actually going to be negative cosine 60, which is root 3 over 2 I hat, and sine 120 is the same as sine 120 minus 180 minus 120, or sine 30, which is half, so it's going to be 5 over 2 j hat, so that I know. Let's similarly do the conversions for B and C. So B is going to be 7 cosine 30 degrees plus 7 sine 30 degrees j hat. So let's write this down. Cosine 30 is root 3 over 2, and sine 30 is half. Keep checking to see if this makes sense. The x component of A is negative, that makes sense. The y component of A is positive, yes. x component of b is positive and y component of b is also positive. We have to get both components of c to be negative because it's pointing in the fourth quadrant. Well, the x component of c is positive and the y component of c will be negative, and we have to get both components of d to be negative is what I meant. So let's see. C is following the same rules. It's going to be 6 cosine negative 45 degrees I hat plus 6 sine of negative 45 degrees j hat. So let's write this down. Cosine of negative theta is the same as cosine of theta, so this negative sign does not affect that. So it's root 2 by 2 I hat, and then negative, because sine of negative theta is negative sine theta, that's negative 6 times root 2 by 2 j hat. So we have found all these vectors in Cartesian form. We are now in a position to add the vectors. Well, why should we add the vectors in the first place? Let's think about that first. The reason being, to find the answer to our problem, the condition that we have to satisfy is that we need that a plus b plus c plus d is equal to 0. That is essentially what I'm asking you to find. So this is converting a verbal problem into a mathematical requirement. What this means is that if I go from A to B to C to D, I come back to where I am. Adding vectors is done by putting the vector in, at the head position of the previous vector, and then you keep doing that till you come back to the tail of the first vector. So that's what we actually need. This can be rewritten as D. If you transfer all these other vectors to the other side, I get D equals negative A, negative B, negative C. So all I now have to do is write down negative A, negative B, and negative C. So I can do all that next. So what I'm going to do is collect all the x components together. If I do negative A, that gets rid of the negative sign there. So I'm going to get 5 root 3 upon 2. Negative B means that's 7 root 3 upon 2. I'm just doing the I hat components now. And this is going to be negative 6 root 2 upon 2. The whole thing I hat. And then plus negative AY, which is that, negative 5 over 2, negative 7 over 2, and then I have negative here and a negative there, so that's going to be positive 6 root 2 over 2, the whole thing, j hat. Well, this can be simplified. 5 minus 7 is negative 2, so I can write this as negative 2 root 3 over 2 minus 2 goes into 6 3 times, so that's 3 root 2, and then this is 5 and 7, which is 12, and then 2 goes 3 times. Okay, couple more steps, I guess. 2 and 2 cancel out, so I get negative root 3 minus 3 root 2 I hat, and this is negative 6 plus 3 root 2 j hat. Well, at this point I'll just stop trying to calculate in my head, and I'll just call it d sub x I hat plus d sub y j hat, where d sub x is this parenthesis and d sub y is that parenthesis. Now, by the Pythagorean theorem, we know that the magnitude is just going to be square root of dx squared plus dy squared. So let's figure that out first. So that's going to be, at some point I'll have to break down and use a calculator. Negative root 3 minus 3 root 2 squared plus negative 6 plus 3 root 2 squared. Now these two negatives actually don't matter, so I did this in my calculator earlier and it turns out to be 6.666. I swear I did not make up this problem, it just turned out to be that, so don't blame me. What I'm going to now do is to find the angle theta. Now tangent of theta as drawn is what I'm trying to calculate. So let me do that off to the side, on this side. Tangent of theta is dy upon dx. So I can write down what that is. It's going to be negative 6 plus 3 root 2. That's what dy is. And dx is this one, negative root 3 minus 3 root 2. And this is where drawing a picture is very important. You observe the numerator is negative because 3 times root 2 is less than 3 times 2, so this quantity is going to be smaller than 6. So that numerator is going to be negative. The denominator is also negative. Two negative numbers when divided by each other is going to give you a positive result. So this, if you put this in your calculator, you're going to get a positive angle. This angle is actually in the third quadrant. So to that positive angle, you have to add 180 degrees. So that's, you have to be careful to do that. So once again, I used a calculator to pull this off, and I get 16.39 degrees for the answer. The true answer is going to be 120, so 180 plus that. So the final answer to the problem is that the person, if it's a person, needs to walk 6.7 units or miles, if you wish, at an angle of 180 plus 16.39, again to one digit precision, that's going to be 196.4 degrees. So that's the final answer to the problem. So basically, to summarize, all problems in vector addition have to be stated in Cartesian form. So if the question is posed in polar coordinates, you have to first convert all the vectors to Cartesian, and then you add component wise, meaning you add the x components together and you add the y components together, and then you get the final result, and then you reconvert to polar coordinates. There is no known way of adding vectors in polar directly. So this method can be followed for just about any problem in both 2 and 3 dimensions. As I mentioned, in 3 dimensions, the only difficulty is that you have an extra term here, and angles are a little more tricky in 3D also. So in this course, we'll stick with 2 dimensions as far as possible.